last, I think, 4 years. I should probably know better, but I don't. The lady from Google started in this area. On the third wave of leadership, you might have heard Girl Geeks from Mel and PG before. I took over roughly in March of last year. And yeah, I've been running it since it's my second year running it. And I'm trying to create more and more partnerships. So you have not heard of us, this is what we do. We are 5 women in this region that want to make a difference. Specifically what we do is we collaborate, we inspire, we build. So we collaborate as many tech companies as possible. We try and inspire more growth. Something we do inspire and try to build more is STEAM. So science, technology, engineering, mathematics, arts, and mathematics. Okay? And we're trying to build a stronger community. So you guys coming out here and working with us here has been great. So I want to say thank you for that. You can join us on Twitter. So this is our Twitter handler and our Meetup account. So coming up in November, we are partnering up with Open Sky Incubator. And it's going to be with promoting startup services. This is our other organizer. Anything that looks kind of nerdy and not funny, that's nice. So yes, that event is Thursday, November 3rd, and that is at Lot 41, closer to kind of down by Fairview. We'll have a whole bunch of startups. If you have a startup that you want to showcase, it's free for you guys. You usually have a logo and actual product demo. Okay. And we'll have food trucks, free beer, and munchies. So you can't say no to that. So Girl Geeks is part of that as well. Again, we're trying to collaborate as many events as possible. And yeah, so I want to say thank you to Introductions KW, Voltmate, and Sorbo for making this happen.
So today we have 2 speakers. I will be the first speaker. I will be talking about putting up my presentation. Augmented reality. Next, Stephen from Startable will be talking about trisecting angles and why it's such an important thing. And also have a small question. Francine and I, we prepared a small questionnaire, so it would be about how you guys do development on your own or online courses or any courses or going to courses, and just we're wondering a bit how you guys are actually doing that. So it would be nice during the break we will be handing out these forms if you could provide us some information about that. Okay, so we'll be quickly first going to my presentation.
Can I just say this is the biggest group ever for Girl Geeks and TW's intersections?
Yeah.
It's collaboration. While she's getting that ready, we do have washrooms down the hallway too.
Okay, so welcome all to my talk, and the topic today will be mathematical concepts in augmented reality. So we all know the big application currently of augmented reality, Pokemon Go. So today we actually will be learning a bit how the mathematics works behind it. So if you have like an image or a video image, how does actually that object get into that image? So my talk will be set of these 4 parts. So first saying quickly what is augmented reality. Next will be next we'll be talking a bit about geometrical transformations, so translations, rotations, scaling, how you actually make those ones happening in mathematics, how to transform an image in a 2D scene, and then finally I will explain a bit how you do 3D calibration with an object. So what is actually augmented reality? So you have a live, direct or an indirect view of the real world, and you want to add in different images. For example, if you are at this place, you want to add in a Pokemon Go, for example. But you also have with surgeries now, like you know, we have currently laparoscopic surgeries, so the surgeon doesn't have that much view anymore. But what you actually also can have done is beforehand, the radiologist will actually make some CT images. They are segmenting structure out of that, and they actually might be putting that on top, for example, of your laparoscopic image, so that the surgeon has more information. So it doesn't have only like the gaming benefit, but you also actually can use it for really life-saving procedures. And the goal of today is actually showing like which types of mathematics are actually involved in augmented reality. You will see a lot of matrix calculations, a lot of trigonometry. You have also algebra, linear algebra, Cartesian geometry, so there's a lot of stuff going on. How will you transform an object in a 2D scene, and then how to let actually object nicely move. So we start here first with an image which you can actually see as a 2D function. You have here your u-axis, here you have the v-axis, and your origin is on top here. And each of these points you actually can represent with 2D coordinates, u and v value, and each of these values represents RGB value. So each color you're representing them with 3 values. And now we want to perform some transformations actually on Pikachu. First one, what we're doing is a translation. So you see we moved Pikachu over 100 pixels to the right, 200 to the left. How are you actually representing this? You have your new coordinate, you accent it, which is the original coordinate plus du, and similarly you have it also for dv. So you can also represent this in this matrix form. You have your original point, you have your new point, and you have your translation values. Similarly, you can also write this p accent equals p plus t, and you can also show this in this nice way. So think, does matrix calculations ring a bell for most people? Or yeah. And it's also important to see here, you here have this plus sign. Next, we go into a scaling of points. So we see nicely over here, Pikachu has grown. So for each coordinate, we actually put them 2 times further in this way. And now you see nicely Pikachu has doubled. How do you represent this? Now we are going to work with a scaled identity matrix. So you have SU, SV here. And if you're calculating this matrix vector product, you have SU times U plus 0 times V, which becomes 0, so you get this SU over times U over here. And similarly, for getting this value, you will calculate this product, this, so 0 times U plus SV times V, and you get SV times V. And in this way, you nicely get this enlarged Pikachu. Last one that you want to do is rotation. We're going to turn Pikachu. This one is a bit more complicated. We will be turning him over a degree of theta, and there you actually have some trigonometry coming on, and you might remember from high school or maybe from university, where you have all the formulas of cosine and sinus of sum of angles. And then you actually get this nice formula. Deriving this one is not that important, but what you actually see here is you have u times cosinus theta minus phi times sinus theta, which you actually see nicely showing up here for the u-accent coordinate, and for the v-accent coordinate, similarly you see sinus theta times u plus phi times cosinus theta, and we're actually happy because you can put this again as a matrix vector product. However, are we completely happy? No, because you see over here you have still this addition, and here you have these two scalings. And what we actually want to have in computer graphics is that this one actually also will become like a matrix vector product, because in that way you will actually be able to speed up your calculations in a good way. So what is going on for here? So we want to arrive at something like this, 3 nice matrix vector products, and then we have homogeneous coordinates. So we actually are going to make a new type of coordinate system. And what are you going to say? We don't want u and v anymore. You actually are adding in an extra coordinate there. So it's like a projection matrix. Does that ring a bell still for people, or? Well, yeah, it's actually just like a way for getting in like a nice way for doing calculations. So what you actually will see, but you also have like the point 1 to 1, 2 for 2, they all will represent the same thing, so they are just normalization you need to do on the z value, and the points on infinity are actually having a 0 value. So what is happening now? So this is what you can remember from the translation. And what are you doing now? This is like a small unity matrix, so you combine these guys 1 times u plus dx times 1. You get this piece nicely here. And a similar way you get 1 times u plus dy times v, what you get nicely over here. And in this way you can actually see that we have similar matrices again, and that we now actually have 3 matrix vector products, which makes us really happy, or computer graphic people really happy. And also the benefit is you actually can combine all these transformations now together. So you can say I do first translation, then a rotation, then a scalation, and you just multiply all those pieces together. And then the benefit is if you have like, you can calculate the product of those transformations, and then you need to do the transformation only once on a point, and you don't need to do all of them separately. So that's a nice way to speed stuff up. Okay, so now we actually get to the nice animation. So what did I do here? Actually, I have here Lego house, which is put over here. Yeah, here you have the V, and I have added in Pikachu over there, and I'm actually going to translate Pikachu, which actually means he will be walking against the sea. Also, you see here, there's here an open door. Pikachu doesn't see the door, but the door will actually feel Pikachu, and then he actually will stop. So for now, actually, I will have just manually segmented where the door is. So said, okay, at this point the door is, and Pikachu can't go further. So if he is there, he actually needs to stop, can't move anymore. But what you actually also could do eventually is like automatically segmenting these doors and everything. But segmenting or delineating things from images will be for the December meetup, so not for now. Okay, so you see, I'm just gonna do that from here. So nice, you see time we're doing, and each time I let him move forward. Here's here at the door and can't move on anymore. And he hurts himself, so he turns straight. Okay. Any questions of this, or? Okay. Okay, so what we now have, the bigger part is, where is, okay. Challenge what we want to solve now is you have like the 3D scene. You want to put like our image of Pikachu or virtual Pikachu, we want to put him in here. How we actually going to work with this. So the challenge is like, this is a 3D world. This is like a 2D or 3D model. And you somehow actually need to align them together. That we actually need to know like, you have indeed not only the problem, you actually need to put them in here, but you also still have the finally your 2D image. How will we actually be able to put all of them together? And therefore, we're going to show what an important equation actually is in augmented reality, and how you actually will be able to perform to find like where this point here actually will be located in the 2D scene. And therefore we also will actually be modeling the camera. So what will be going on? So I built this nice calibration object, but actually also is like called the chess pattern object. And what will I be doing here? I say, here's my x-axis, my y-axis, my z-axis, and I will be putting in all different points here, which I know actually where they are located, because I know the dimensions of these Lego objects. Lego objects are built in a really conform way that if you in 10 years will put here in a new build Lego object, they will still nicely fit together. So in this way you nicely can say which are all the different locations of these points. For example, here we are following this nice point. Next you see a picture of this calibration object. You see the point again here. You can nicely see you have U here, so you can, or starting from here, you know the U coordinates, from here, you know the V coordinates, and this is done for a lot of different points here, and then you will be calculating this connection, and I want to see the location where I actually can put Pikachu nicely over here on the table. So, what do I need to do for that? So, if you're thinking, building a camera, you have two parts. You have your 3D world, the camera sees, but actually what you eventually see is like a 2D scene. And this is what will be modeled in here. But what you also still have, like, your camera is not at the same time all the time, so you always will need to see where is actually my location of my camera towards the real world. So if you would be thinking, for example, with Pokemon Go, you're looking through your phone and you have like the image what you see, with your phone you know which GPS coordinate you have. You also with your gyroscope you know which angle you're looking at, and in that way you can actually, the camera or your phone knows which part of the world you're looking at. And so this is actually what you have here, that you're calculating actually a rotation and a translation. So if you're looking here, looking at a different scene, so if you're looking there, so that's what you calculate with these parts. And this one is actually the camera model. So here you see the X, Y, Z coordinates. So we have this point where it will be located actually in these points. And again, you can actually multiply these things and you get a P over here, which will actually be the matrix that we will be looking for. Okay. like I said here, you're looking which part of the camera that you actually will be seeing, and with Pokemon Go you have it to your GPS coordinates, with your gyroscope. We will be actually modeling this ourselves by putting points. Okay. So what is the camera now actually doing? Like you know, you have the 3D world coordinates in your camera. You only see 2 of them, which you actually do nice projection here. But you only end up with 2 coordinates. What you then also see, the world is smaller on a picture than it is in real life, which you actually nicely see modeled over these 2 places. Okay? This is, yeah, still too hard a mathematical slide. Sorry. So you have over here, you have, so this projection, that you go to your 2D coordinates, you have your scalation, and then you have over here, because your camera is not like a real nice pinhole camera, so you need to make up for some factors, and in that way you do some extra formulas. Here you do fx and fy, and then you actually have this information that you need to calculate for your camera, and then you actually know your 3D world camera, how your points actually will be modeled out. And if you know all these values, you actually will say that your camera is calibrated internally. So if you have a picture, you actually can nicely know where everything is. And these are these nice values over here. You have the rotation and translation, and that actually means like your camera is calibrated externally. Here you have 5 values, here you have 6 values. So there are actually 11 parameters that you will need to know when you want to combine and you want to know the transformation from real world to your 3D coordinates. And now what? Does anyone know this picture? No? No Kinect fans here? So this is actually, if you're setting up your Kinect camera, for example, at home, you will need to make a picture of this one, and your Kinect will actually calculate the calibration so that you nicely can transform actually points, your objects, into your real world scene. So if you're playing a game and the fancy skull or something is showing up on your face. So this is this thing that actually helps for this, for putting it in a nice location. So similarly, this is my object that I use for this calibration. So manually added in a lot of different points. You're looking for 11 parameters, so therefore you actually need to know at least 11 of these different points with the correspondence in this image. And this information. And so we have again here this nice thing of the internal and the external camera. Because I don't have this information separately, I actually will be building this slightly nice 3x4 matrix. And now in this case, actually the M values will be my unknowns, and my U's and V's and my X, Y's and Z's I actually will know because I have measured all of these. And you have this guy over here, UI, U combine, again this matrix, this vector product, get this over here, same one this time here, put it over there, and then you have the 1 here, this actually equals 1, and therefore you put both of them here in your denominator. We are interested in actually these values, so the amps, different amps. So, and you can actually write this one nicely introduced this system of equations. You put this in for at least 11 points. I eventually worked with 20 or 25 points, measured all of them, put them in the equation. You can work with nonlinear regression. You will get a nice matrix for this. And nice result eventually is that Pikachu gets where he needs to be. And yeah, I put him on a small one, but it was nicely there on the table.
So for Kinect, I guess you have APIs that helps you to do
You have
this.
APIs that is done automatically for you, but then also you can do it. You also see like exists a lot of literature also where people try to have better calibration algorithms because they say like what is currently available is not good enough for their applications. So if you actually will look, there's a lot of research available about how to calibrate the Kinect. The reason also behind it is because it's like cheap hardware also to use to get, so it's easy to do research for that, but there's a lot of information available, and you can even just program with the Kinect yourself, and then you just can say, okay, I want to actually get Pikachu on this place in real world, and this will be automatically calculated for you that he also will get there in that place. So normally if you're programming, you don't need to do all this stuff, but it's just fun a bit. You see how stuff actually are happening behind the scenes. Okay.
And Kinect has internal and external camera?
I think it's just like the one that you put on top on your television or before your television. So it's, I think it's, I don't know whether it's one or two. But it's like, it's separate from the Kinect, from the Xbox itself, so.
But that one looks like an external one, isn't it?
Yeah, it's an external one, yes. And, but also like if you see like, if you want to know like those values of the camera itself, they're also are known actually for Kinects, but so if you don't care that much about accuracy, you can use those ones, and otherwise you can actually do some own calibration also yourself. Okay. So these were some of the books I used. It was the transformation of the coordinates was explained nicely in the book of my professor from Belgium. And then this is a book I used for studying computer graphics. This is a nice presentation. I don't find the reference of it anymore, so therefore I just call it by its name. And here you have nicely how you can actually represent the different coordinate systems, and then here a nice paper if you want to read more about the different ways of calibration. And all my implementations were done in Python, with NumPy and SciPy. And all Pikachus and Pokemon are still alive. Okay.
Do we have any questions? Anything about augmented reality?
So I guess HoloLens has the same principle, yeah?
Yeah. And also it might be that they have more cameras available, so then the calibration actually will be more complicated, that you don't only can represent it by just a small pinhole camera.
So if the values are constant across, like if values don't depend on moving the camera around or whatever, would it be possible just to calibrate once at manufacturing and then be done with it?
Yeah, it also might be true, but it just might be like over time that things are changing a bit, but yeah, that's true.
Do this apply to virtual reality? Because I've seen like virtual reality applications where you have all kinds of
Yeah, indeed, and they are also trying to
Sensors
like where
and
they are
stuff.
located against the 3D world, so that they also know like how they need to. So indeed, you have like the equations that you're modeling are the same. The difference is just like you only have a virtual world, you don't have a 3D real world available with it. Yeah.
So with your calibration object, do you have to take the picture and then like manually mark all the points on it?
So indeed, that's the way that I can indeed currently do it now. Like, but you also have actually like segment computation algorithms, for example, that are checking like where the gradient is deviating, that you know where the corners are. Or you also, for example, might have like that you're mapping the image with the 2D image to check where you actually are located,
Okay,
and in
yeah.
that way they are indeed putting up all the different markers.
But for your Pikachu, you did this all manually?
I did it all manually.
How long did that take?
It was like a few minutes. The problem was only like initially, like I had like a nice 3D cube and I was working on it and it didn't match up, and I was thinking, oh my god, I was wrong. I will be making a smaller object maybe that might help out. And what I then actually saw was it actually did help out, because what I saw here was nicely Samsung written, and I did something wrong with actually showing my picture in the beginning, so I had my Samsung over here, and then I saw, okay, that's the thing what is going wrong. My accents are not really matching up, so then actually my problem was fixed. Indeed, the sad thing was like, therefore I actually destroyed it. Needed to break my whole cube because indeed I didn't have that much white and blue Lego blocks. But yeah, that was a bit of a challenge, because firstly I was very ambitious in putting in all the points, didn't get a good result, and then it's just like you need to make sure that you put your points in the area where you actually want to model it, then you get nice results, because probably also like just a matrix or linear model is not the best